I mean, not वैसा नहीं like code as in कैसा मतलब ODE कैसा एक एक मोटो मॉडल के लिए ODE था वो
सबके पैरामीटर चेंज करता है
हम लोग क्या
तेरा मिनिमम कट ऑफ ईयर होगा पार्ट 2 का हां मेरे को दिखा रहा है अपना एला शेड्यूलर आएगा
नहीं कोई शेड्यूलर नहीं बिना शेड्यूलर के साथ काशी पर किया भाई शेड्यूलर बस भी नहीं ये बुक 2 मिनट में चल रहा है तो शेड्यूलर डाल के
कितने कोड डाले
पता वही
10 था यहाँ पे 10 चल
चल
Oh, what about the Zoom? Are there people on the Zoom?
इसको चेंज करना नहीं था
Make sure that
थोड़ा बहुत अपना वो डालना था कोड का वो मैंने डाल दिया अडैप्टिव कोडिंग का दिया है इसके
Okay, cool.
मैं ऊपर ले गया इसको 512 ले जाना मैं थोड़ा
Okay, we can start. Okay, hi everyone. Am I audible to everyone back there? Okay, so today's recitation is going to be about verification, and this is sort of like a part 2 to last recitation, which was about classification. I'm Prakriti, and this is Arjun, and we're going to be taking this recitation today, so let's get started. So we're basically going to go over like 4 main objectives. First, we're going to go over what verification actually is. Then we're going to describe the verification task and specifically what we require you to do in homework 2 part 2. Then we're going to go over some verification optimized approaches. And then finally, we're going to give you some tips and we're going to run through the verification part of homework 2 part 2. So first, we're going to talk about what the verification problem is. So if you guys remember from last recitation when we talked about the classification problem, we mentioned that classification is essentially like a supervised learning method, which learns a model that predicts a class given input data, right? And in that same way, we require you to do face classification for homework 2 part 2. And so essentially what we require you to do is to determine who it is in a given image. So we want you to map an image to one of n classes. But verification, on the other hand, is more of a matching operation, where you match a given sample to say the closest sample from a reference of n other samples. That can also be looked at as like a one-to-one matching kind of task, where we want to verify if 2 feature embeddings that you will derive from your input images are similar and whether they belong to the same class. But it can also be extrapolated where you have one image and you have like n other images that you want to compare to, and you want to find out which of those images your input image is most similar to. So it doesn't necessarily have to be a one-to-one mapping task. And the key thing to note is that you guys have to define what you measure as closeness over here. So we will go over that further in the recitation. And so, yeah, before we continue, we're going to discuss the closed set and open set problems, which is on the next slide. So basically, in a closed set task, your test samples must come from one of the classes that are predefined in your training set. And this is also something that we talked about in the previous recitation. So that means that at test time, you are guaranteed to see a category that you have seen before in your training data set. And so this is different from open set classification, open set problems, where the test data has samples from categories which are not necessarily defined in the training set. So at test time, your model can be shown images from a category which it has never seen before. And so as you guys can see over here on the slides, in the closed set problem, your model essentially learns boundaries which separate a class from other classes, whereas in the open set problem, your model learns tight boundaries around the classes that are shown in the image. So as you guys can guess, classification is closed set, since we have a fixed number of classes, meaning that all the images in the test set must be in one of the classes defined by the training set. And then open set is a verification problem. Or open set is used in verification, where some of the images in the test set may not be present during training. So essentially, face verification is part of that class of problems, where you're given an identity, and at test time, you'll have to compare it to n number of identities that you may not have seen before in your training set. So how can we use a classification network for verification? Essentially, what we can do is we can compare closeness with all of the classes from examples in your training set. So you will be given two images, and you will have to tell whether they belong to the same class or not. And so you would essentially have to define some sort of similarity or some distance metric between these embeddings. And you're going to have to define a threshold that says, okay, if their cosine similarity or something like that is below or above a certain threshold, then you're going to say that either they belong to the same class or not. And so that is one of the key things that you have to implement in this homework. So now we're going to talk about whether the embeddings that you actually get from your training for classification is good enough for verification or not. So, we will be able to get linearly separable embeddings, but is that good enough for our verification task? And that's not necessary, as our linear layers in our classification task can learn arbitrary decision boundaries, but it doesn't necessarily guarantee that the intra-class distance is smaller than the interclass distance, which is essentially what we want for verification. So although we may get a model that is linearly separable for known classes, we won't know what it'll necessarily do in unknown classes because we're not training it on that space. So it may not be good enough for our verification task. So what essentially we require is discriminative features, where we know that the embeddings of two pictures of the same person are always closer than those from pictures of two different people, which we may not necessarily get if we're purely training for the classification task, as you can see here. So now we're going to talk about how exactly are we going to get these kind of embeddings or these discriminative features. One thing to note is that we have to change the way we train, and not just train solely for the classification task to get the embeddings, but we need to explicitly try and get the embeddings that are discriminative. So our final loss function captures what it means to be discriminative. So we want to use a loss function that strongly correlates with that task or evaluation criteria. And cross-entropy loss was a good choice when we were evaluating multi-class metrics, but for verification, where we have this added requirement of discriminative features, we need something more tailored to this problem, and that's where contrastive losses come in.
Right, so let's talk more about contrastive losses and how they work. So to begin with, we're going to consider a triplet loss. So what you're trying to do over here, as you see in this equation that makes so much sense, is that you're trying to compare a set of input images with respect to an anchor. Now, I'll go over the terms about what an anchor is, what a positive is, and what a negative is. An anchor is a point of a person who you know the identity of. A positive is the same person, but a different image of that person. And a negative would be a completely different person altogether. So in an ideal world, the positive and the anchor would be close to each other, and the negative would be very far away in whatever plane that you're trying to optimize in. So the way that we train this network is that we're trying to make it project into a plane where your distance between your anchor and the positive is less, and the distance between your anchor and the negative is more. When I say distance, I do not mean Euclidean distance or any metric like that. It depends on what plane you're working in. All right, so let's talk about other contrastive losses. And so here are a few that we recommend that you can try out. So let's talk about how you're going to be using that in your verification approaches. Right. So just to reiterate the problem, we have an open set problem over here, in the sense that we do not know all the identities that were not there during training. And so now we have to find out what the query person is with respect to our training set data that we have. Right. So for the time being, as you would have trained, if you've already started working on part 2, you would have seen that you have a CNN, which gives you a feature. And that feature vector basically is fed into a linear layer, which gives you the classes, and that is your classification task. But now let's talk about verification. You have these features, and these features are basically the network's attempt at trying to separate different faces in this hyperspace that we're working with. And so for our case, we're going to put in input image over here, get its corresponding feature vectors, and then we have a face database which has all the features of the other people that we're working with. And our end goal is to find out what our input feature vector corresponds to with respect to the feature in the face database. Does that make sense? I will take that as a yes, unless if you have any doubts, please feel free to stop me. All right. So once we have our feature matching algorithm, which depends on what you're trying to do, you would have an ID. So now how do we use all of these fancy loss terms with respect to our problem over here? So you could have, we recommend using two different approaches. You can also come up with other approaches depending on what you find and if you think that is appropriate. The first is joint loss optimization and the second is sequential layer integration. So let's talk more in detail about what we're trying to do here. So effectively in joint loss optimization, you're trying to optimize for your classification and your verification simultaneously during training itself. It's the same training loop that you have, and you're trying to calculate the loss for your labels and also for your verification. And effectively, your total loss is a combination of both of these losses. So if I were to give you a snippet of some code, so you would have the cross entropy loss from your classification, and you would have some triplet loss from your verification task, and your effective loss would be a combination of both of those losses with respect and some weighing factor. Now these are again hyperparameters that you can tune and see what works well for your use case. Depending on what model you're using, you would have to change these values. All right. So that's what joint loss optimization is about. Now let's talk about sequential optimization. So once you have your trained model for your classification, you get a set of feature vectors from that. Now, what if we were to train a separate network altogether, which takes in these features and tries to project it into a space where they're so far apart that all the similar classes are together and all different classes are like different identities are far apart in whatever plane that we're working with. So we get our embeddings from the model, and then we use a contrastive loss, which basically tries to maximize this distance further, depending on the pre-trained embeddings that you're getting. So you could put in possibly an arc margin product, which basically takes in these embeddings and projects it into a spherical, onto a sphere. And effectively, you're trying to group all these similar identities together on one end of the sphere, and separate identities on, like, let's say if there were only two people, two different people that you're trying to classify, it would be ideal if you had one set of people on one end and the other set on the diametrically opposite end, because that gives you the maximum distance between the two. And so over here, effectively what you're trying to do is a similar thing except for a larger number of people. So how you would train this is that you would take in your feature vectors, which you've trained from a classification model, put it into a arc face layer, which projects it in, which does a few operations on the embeddings to project it into space. And then whatever output you get over here, you do a backprop on with respect to the corresponding loss. And so over here, the loss would be the arc face loss and not anything else. Right. You want to talk about the data set?
Okay, so now we're going to quickly cover what the data set that you're going to be working with in homework 2 part 2 is. So if you guys have read the write-up, you know that it's a subset of the VGG phase 2 data set. These images are essentially downloaded from Google image search. And the reason we chose this data set is because there's a large variation in factors such as pose, age, illumination, ethnicity, profession, etc. There are 7,000 identities in this data set, and we also ensure that these data sets are class balanced. So each class has an equal number of training images, and all the images are resized to the size that you see up there. So your aim is essentially to learn to classify images with in your classification task with the correct face identity from 7,000 different identities, and in this verification task, given an unknown identity, which known identity is it the closest to? So yeah, in your verification task, you have a test set, which is a balanced set of 1,000 known identities and 1,000 unknown identities. And your task, as we mentioned before, is just to find the similarity between each unknown identity and all the known identities. And then you want to predict the class with the highest similarities, as you can see in the picture there. So we're just going to give you, once again, a quick overview of homework 2 part 2. This was all covered in the previous slides, but we just outlined this here once more so you guys get a clear idea. So your objective is to solve an image-based verification problem using a CNN. The scenario at hand is verifying faces and images. And one of the reasons why we used a CNN, and this was also covered in the classification recitation, is because pictures of faces, as you may know, have indeterminacy of position, and CNNs are position invariant, which is why they're very good for this particular task. This is an open set problem, as we covered before, and the only real requirement is that based on whatever distance metric you do choose, the embeddings of two people of the same person are always closer than those from those embeddings from images of two different people or people from different classes. So yeah, this face verification problem is also from a larger class of problems, and this is also outlined in the write-up. So for example, we have information retrieval. So Google also allows users to search for images using an image as a starting point as opposed to like a written query. And also speaker verification, as a speaker's voice does contain like unique traits for that speaker, so it is possible to identify them simply based on their voice. And so in all of these problems, the common trait is that you're given an example of a category of data, and you're given something known as a probe instance, and you essentially must determine if your example and the probe are from the same class or not. So we're going to discuss two different approaches to face verification. This was also outlined in the write-up. So the first approach was to use classification, where essentially you put images into categories based on the closeness between their feature vectors based on some metric. And so since classifying an image into one of several classes also requires the model to extract discriminative features, why not just use this for verification as well? And since images of persons with similar features will belong to the same class, this would be a good metric to use for verification. And so essentially you could just perform multi-class face classification, where the input to your system will be the image of a person's face, and the model will predict the class that an image belongs to. However, we also noticed that crossing the high cutoff for this classification task does not imply that you will cross the high cutoff for face verification. And this is because, as we discussed before, we produce feature vectors that are linearly separable by optimizing the network using cross-entropy loss in our classification task. But this does not optimize for direct comparison of two instances to see if they belong to the same class or not. Because as we talked about before, when we talked about intra-class distance and inter-class distance, the distance between feature vectors belonging to the same class may be greater than that distance between features in different classes. And this is not something that minimizing cross-entropy loss will allow you to fix. So we suggest some loss functions for you guys to use, like center loss, sphere loss, etc. And you can train these jointly with cross-entropy loss to get high-quality feature vectors. And we do recommend that you go through the papers that we have linked in the write-up and learn how to code these on your own.
Right, so just to give you an overview of what we're trying to do in verification. Usually the approach to do verification is that you put in two different images and you get a similarity feature vector of those two images and try to find a similarity between those two images. And so you put a hard threshold on if the face is the same person or not, and based on that classify that person as to if that is the same person or not. But that is not what we're doing over here. We're trying to do over here, our problem statement is set up such that we're comparing one image to all the other images that are there, and for the image that we have the highest similarity with, we give that query image that particular class. Right, so similarity metrics. So like Prakriti defined before, you could either use the Euclidean, you could either use the classification task itself, the features that you're getting over there, or as I explained before, you could put in a separate layer or put in other fancy losses in front to do that. So if you're trying to use the classification features as your discriminative features for verification itself, you could use either a cosine similarity or Euclidean distance to find out the difference between two feature vectors, and based on that, classify a particular query image. And this usually works well, but like Prakriti said, a good classification performance does not relate to a good verification performance necessarily. So you are encouraged to try out a different loss function for verification and different approaches for that itself. Yeah. Right. So when we talk about one-to-many comparisons, like I said, based on the similarity metric that you're using and how you've trained the network, your performance will vary greatly for verification. And so, as explained before, you're doing one-to-many comparisons. You're comparing one query to all verified identities and trying to find out what that feature vector from the query image resembles to in the database that we have over here. So yeah, a few functions that you can, loss functions that you can try out is center loss, fear phase, and cost phase. These are papers which are available on archive. A few of these approaches were developed here at CMU itself. So yeah, feel free to talk to Professor Bhiksha about it because he's an author on one of these papers. And yeah, I think that's all for the verification and classification task. We'll now open the floor to any questions that you may have.
So I'm a little confused. So what was the embeddings block doing?
You mean over here?
Yeah.
Right. So the embeddings, you have a feature vector that you get from the classification network, and you put them into another layer. Now these layers provide an embedding. So it's a separate hyperplane that you're projecting these feature vectors in based on some mathematical operations. And so that is a embedding that you get at the end of that layer on which you try to do backprop on and optimize. So if I talk about here, the out over here, which you get after the arc face layer, would be an embedding of that particular feature vector.
So do we always use our margin products? So like, is that like a...
Yeah, so this is just an example. You can try out different other approaches that we've explained before. So you'll have a bunch of different embedding layers, and you'll have different losses for those embeddings. So you'll have to try out which combination works well. Not everything goes with everything. So be careful when you try to.
So could we use a different embedding with the different loss?
As long as both of them kind of are optimizing for the same purpose, yes.
Okay. And also I had another question. So could you go back to the previous slide? Like back?
After this?
No, like there was another big block diagram, like where you said, yeah, here. So so do we have use both the cross entropy loss and the contrastive loss together to get like sum it up to get a one final loss?
Yeah. So you're trying to regularize the network to optimize for two constraints altogether. So this is very common in like tasks like this. This is a side note. For multimodal machine learning, you'll have 10 different aspects that you're trying to optimize your network for. So you can't just use one loss function and expect the network to perform because it will just learn from that particular loss function the task that you're trying to obtain from that loss function. Over here, since we're trying to optimize for classification and verification, you'll have two different loss functions, and both of those impose their own constraints on how the network is trained.
Okay, so here, like in your pseudocode, then like how do we define, I guess, the anchor or the positive or negative? Like, how do we define them? Like, do we select one particular?
Yeah. So you basically you kind of set the entire problem in such a way that you know the anchor and the query image that you're putting in, and so based on that is when you can like do a triplet loss over here.
Okay. Okay, thank you.
Can you probably train for verification and say that it will work well for classification as well?
Not exactly. No. So so to get to verification, you would first need feature vectors, which you would get from classification. It becomes a chicken and egg problem then. But let's say if you had some features, the intermediate features, which you have from an untrained network, which you get, you can probably train the entire model just on verification loss. But there are two things that you might want to consider. One is those features that you're getting are not really representative of what the input is, and like you're not it's not separable in that hyperplane. So even though you train it, you might not be able to get proper separations. And the second thing is, since we do not have enough data on that front, if you have a huge model, you'll overfit definitely, and then your performance will be bad. Any other questions? Yes.
When will these slides be on the website or on Piazza?
Yeah, they'll be posted on the website, the video on the slide.
So by end of day today.
Okay.
So what's the logits line doing here?
So the logits is basically the classification loss that you're getting. This comes in from the linear layer that you have at the end of it.
Okay, cool, yeah. So how much we like take the weights for each loss? So here you said it's 70% and 30% like weightage. So do like we just mess with that?
Yeah, it's a hyperparameter that you have to tune for.
Yeah.
Yeah. If there are no more questions, we will call this an end to our recitation, and we'll be here to ask for your. If you have any questions, we can take them offline. All right.
Thank you, guys.
Thank you.
Yeah.